A student recently asked a practical question about how R handles information. Can a simple vector hold direct references to other vectors as its elements? To test this, we can set up an experiment. We'll assign two sequences of numbers to individual atomic vectors, A containing 1 and 2, and B containing 3 and 4. When we combine them using the C command, it's natural to expect a nested result, one container holding two distinct elements. Instead, the system merges the elements into a single sequence, 1, 2, 3, 4. The atomic vector type is designed to concatenate data into a flat line, which means the original structure of A and B is lost. For data analysis, this creates a challenge. If atomic vectors always flatten their contents, we need a different architectural mechanism to build and maintain complex hierarchical datasets. While flattening basic vectors is a language design choice, R's memory management follows logic established by pioneers of modern computing. This hardware is part of the von Neumann architecture. It established the concept that a computer's programs and its data share a unified memory space, where every piece of information has a specific address. R adopts this logic through bindings. A variable name isn't a container holding your data. It's a label pointing to a specific location in that shared memory space. The solution to nesting is the list command. Unlike atomic vectors, this generic vector holds different data types without merging them. It preserves original vectors by storing only references, a collection of bindings pointing to the memory addresses where the vectors actually live. Because a list is a tree of memory bindings, it fulfills the student's original goal. It effectively allows a single object to hold and organize multiple other vectors, completely without destroying their individual internal structures. This model introduces a specific risk. If multiple names point to the same object in memory, changing data through one name might unintentionally alter it for the other. We observe this with the trace_mem function. Run on a shared vector, it displays a hexadecimal tag, the exact memory address. If we modify one shared variable, the conflict is avoided. The console shows R assigns a new secondary address to the variable we're editing. This is copy on modify. To keep your data safe, R automatically creates a private duplicate of an object the exact moment you try changing it. This is the default for almost everything in R, though environments are a notable exception. They use reference semantics, meaning they are modified in place without making safety copies. Copy on modify allows R to share data objects efficiently while removing the risk of accidental corruption found in languages that use direct pointers. Because lists are trees of memory bindings, getting your data back out requires specific operators. Easing the wrong one is a common source of errors for new analysts. The double bracket operator reaches inside the list to pull the raw element out, used when you need the vector itself. The single bracket is different. It slices off a section of the container, returning a sublist that keeps the data wrapped. You'll also see the $sign. This is simply shorthand for the double bracket operator, providing a more readable way to reach an element when it has a name. Distinguishing between the sublist and the raw element is essential. If you try to run math on the list container instead of the numbers inside it, the code will fail. These mechanics are the basis for the most common structure in data science. Imagine a list where every element is a vector, and every one of those vectors has the exact same length. When these vectors snap together, they form a data frame, the primary structure R uses to represent data tables. We can confirm this by checking the type of any data frame. Even though it looks like a table, the type of command reveals that underneath the surface, it is a list. This internal structure is why data frames can handle different types of data, like names, ages, and dates, side by side. Each column is simply an independent vector bound within a central list. Understanding these memory bindings makes complex data manipulation predictable. A data frame isn't a unique species of object. It's a generic vector wearing a rectangular costume.